Hi, my name is Victoria, and today I'll be going over a few questions from general physics. So the first question we have is dimension analysis, and the first thing it asks is that we look for variables A and B. So the first thing we're going to do is break down the equation that's given, and that is A equals K times P times V squared. So P stands for pressure and V is volume, and so we're going to break down this even more because pressure and volume actually have their own dimensional analysis. So that's going to be K times mL to -1 times T to the -2 times L to the power of 6. So now that we have a full laid out dimensional analysis for this equation, we're going to have, or for the variable A, we're going to get our answer and bring this all together. So that will equal K times the mass times the length to the power of 5 times T to the -2. And that is the dimensional analysis for the variable A. So now for the variable B, it's the same concept. We're just going to have B on the other side of the equal sign. So that would be B equal to K times L to the 3rd power. So these would be the two-dimensional analysis for the variables A and B. Now for the next question, it's actually a lot more simple. So it's asking us to determine the x and y components of each of the force vectors that's given. So for A, it's giving us a vector of 12 newtons at an angle of 60 degrees. Our angle is equal to theta, and our x and y components are always equal to cosine and sine. Or not equal to, but that's how, these are what is going to help us find the components. So for A, we're going to use cosine to find x. So what we're going to do, we're going to put the force of the vector times cosine theta, which is 60, and that is going to give us 6 newtons. And we're going to do the same thing for y, except instead of using cosine, we're going to use sine. So it's going to be 12 times sine times 60, and that is going to give us 10.4 newtons. So for B, we're going to work out the same, it's going to be the same way. The only difference is now that instead of our x component being positive, our x component is negative. So that being said, when we figure out the x component with this equation, it's always going to be negative. So it's -15 cosine 20. That's equal to -14.1 newtons. So for our y component, it'll be the same thing because our vector is actually still positive for the y component. So it's 15 sine 20. That equals to 5.13 newtons. Lastly, we have our C, and in this case, our y component is actually negative, and our x component is positive. So instead of multiplying the negative by our x equation, we're going to do that with our y equation. So for x, everything will stay the same. It's the force times cosine times theta, and that gives us 21.7 newtons. And so since our y component is negative, it'll be negative 25 times sine 30, which equals to negative 12.5 newtons. For our third problem, we're given the equations and we're going to find various, figure out various questions. So the first question is asking us for the time the ball was in the air. And the information given is our initial velocity, which is 60 meters per second. Our theta is 20 degrees. And our teammate is standing 100 meters away. So for the time the ball is in the air, our equation is going to be t equals 2 times the velocity times sine theta over g. So now with the information given, we're just going to plug it into our equation. So 2 times velocity, which is 60, times sine theta, which is 20, and gravity is our constant, which is 9.81. So we input that into the calculator and we get 4.18 seconds. For the second problem, it is asking us for maximum height. So in this case, we're looking for the equation given would be v squared sine squared theta over 2 times g. So we're going to do the same thing, input all of the information into the given form equation, which is 60 squared sine squared 20 over 2. G is our constant, and that gives us 21.5 meters. For our third equation or problem, it's asking us for the horizontal distance it travels before hitting the ground. So that would be our range. The given equation is v squared sine 2 theta over g. So we're going to do the same thing, just input all of the information given, which is going to be 60 squared times sine 2 theta, which is 20, over 9.81. So now we're going to input this into the calculator and we get 235.9 meters. So the fourth question is asking us if our teammate actually receives the ball, and the information given says that he is standing 100 meters away from us, and our range says that the ball hits the ground before at 235.9 meters. So that says that our teammate actually does not meet the ball. So now lastly, the last question is asking us, what should your teammate do so that he can take the ball before the opposite team player takes the ball? If he runs, will he run backwards or forward? And at what speed does he need to run to take the pass? So here, we obviously know that he is going to be running backwards. So our teammate needs to travel 135.9 meters backwards at, oh, now we have to find out the speed he needs to run. So speed equals distance divided by time. So our distance, our range he would have to travel in this case would be 135.9 meters divided by our time, which is 4.18 seconds. So we input that into the calculator and we get 32.5 meters per second. And that is problem 3. For our next problem, we need to figure out, we are given actually the equations we need for this problem. So the question asks, how far in front of the Explorer should Alex drop supplies? So it's saying that while the plane is flying horizontally at an altitude of 2,000 meters with a velocity of 150 meters per second. So this would be, we're going to figure out how far in front of the Explorers the Alex needs to drop the supplies. So the information we know is the velocity, which is 150, our y component, which is 2,000 meters, and we are looking for our x component. So in this case, we would do negative 2,000 initial velocity is 0 plus half of the acceleration. In this case, we're using gravity, which is 9.81 times the delta t to the power of 2. Now we're going to simplify this equation. Negative 4.19 times delta t squared. So we're looking for the change of time, so that way we can actually find our x component through another equation. And we'd have to manipulate this equation so that this is on the other side of the equal sign. So delta t squared equals to 2,000 divided by negative 4.9. Now to get rid of this square, we just square the other side of the equation, and that equals to 20.2 seconds. So now we're going to use another equation so that we can get our x component. And that other equation is the velocity x equals to the change of the displacement over the change of time. So here we're just going to plug in the information given. So our initial velocity is 50. Displacement divided by our seconds, which is 20.2. So we plug that into the calculator and we get 3,030 meters in front of the explorers. So question number 5. Question number 5 says a 3.5 kilogram block on a smooth tabletop is attached to a string to a hanging block of mass of 2.8 kilograms. The blocks are released from rest and allowed to move freely. Find the acceleration of the blocks and find the tension of the string. So in this case, we would use two different formulas. And this tabletop is T minus mu R to equals to the mass times acceleration of block A. And this bottom one is mass times gravity minus T equals to MBA. So for the first equation, or for the first problem, it's asking us to find acceleration. So we would do .8 because that is the given mass times gravity, and that is giving us our weight over the combined masses of both of the weights, or of the blocks. So if we input that into the calculator, it'll be 4.356 meters per second. So that would be the acceleration of the blocks. B states that we need to find the tension of the string, and T here in these equations are actually for that. And so we would need the acceleration that we calculated here, and the weight of the two different blocks. So for the first one, we're going to multiply it by the acceleration. Multiply the acceleration by the mass of the block, and that gives us 12.19. And the second one times 3.50 is equal to 15.25. So if we add those together, that is the tension for the string. Moving on to the next question, we have the Atwood's machine, and it consists of two masses connected by a string that pass over a pulley. In specific case, mass 1 is 3.1 kilograms and mass 2 is 6.4, and we have to find the acceleration. So here we're gonna multiply the second mass times gravity minus the first mass times gravity, and we're going to divide that by the mass of both of the blocks, and that equals to, let's simplify that more. We're going to do 62.7 minus 30.4 over 9.5, and we get 32.373 over 9.5, which equals to 3.41 meters per second. And that is how to find the acceleration for the Atwood's machine. For our seventh problem, we're going to find the magnitude of the impulse that the plate gives on the bullet. So in this problem, it says that the super dart of a mass 30 grams is traveling at 250 meters per second. It strikes a steel plate at an angle of 30 with a plane of the plate as shown in this figure. It bounces off the plate at the same time, at the same angle and speed of 250 meters per second. So it's asking us for the magnitude. So in this case, we would multiply, we would change this into kilograms instead of grams, so it'd be 0.3 times the velocity, which is, the velocity, which is 250, minus, we're gonna actually find the final velocity, so we're going to subtract the final and initial velocity, and we're going to multiply it by cosine theta, which is 30. And now we're going to break down this equation more to find our x and y components. 0.3 times 0 times cosine 30, and that equals to 0 kilograms times meters per second. And for our y component, it's equal to 0.3 times 250 minus negative 250 times sine 30, and that gives us 50, or let's simplify this, so it'd be 0.03 times 500 times sine 30, which equals to 50 kilograms times meters per second. And that would be our magnitude impulse that the plate gives off to the bullet. So for the last 3 questions, question 8 is asking a 0.080 kilogram pet lab mouse sits on a 0.35 kilogram cart as shown in the figure. The cart is at rest as is a second cart with a mass of 0.25 kilograms. The mass now jumps to the second cart. After the jump, the 0.35 kilogram cart has stopped at a speed of the initial velocity of 0.91 meters per second. What is the speed of the second velocity of the mouse and the 0.25 cart? So in this case, we are going to have to find the velocity after the mouse jumps. So we're going to multiply 0.35, which is the mass of the cart, and the initial velocity, which is 0.91. We're going to add that to the second cart, which is 0.25, and we're going to add that weight of the second cart with the weight of the, or the mass of the mouse, which is 0.080 times the second velocity. So here we're actually going to have to simplify it. So we're gonna equal the equation to 0 and simplify. These two is equal to 0.32 plus 0.33 times the velocity. So now we're going to have to manipulate so that we get the V2 isolated. And that would be, we would move this to the other side of the equation, which makes it negative. And that equals to 0.33 times the velocity, the second velocity. So now in this case, we would just have to divide 0.33 by both sides of the equation. And that would give us this equation so that we could find the value of the second velocity, which is equal to 0.97 meters per second. And going on to the next equation, or next question, sorry. This one is asking, a 5 kilogram metal ball at rest is hit by a 2.0 kilogram metal ball moving at 4.0 meters per second. The 5.0 kilogram ball moves forward at 2.0 meters per second, and the 2 kilogram ball bounces back at 2.0 meters per second. So it's asking to find the total kinetic energy before and after the collision, and how much energy is transferred from the small ball to the large ball. So here's what, here's the equation that we're going to use. And, so it's kinetic energy, which equals to half the mass and velocity squared plus half of mass 2 times velocity 2 squared. So now we're just going to use the given information to plug it into the equation. So it's half times 5.0 with no initial velocity. Oh, sorry. We're going to do half of 2 times 4 plus half of 5. And that is going to give us 16 joules. So for the next equation, it'll be the same equation, just different numbers. So it'll be kinetic energy equals to half of the mass times the velocity squared plus half of the second mass times the second velocity squared. So now we're just gonna plug this information into the equation, and that is going to be -2 plus half of the second mass, which is 5 times 2. And that'll equal to 8 joules. So the last question is asking how much energy is transferred from the small ball to the large ball. And in this case, that would be we're going to follow this equation, which is the kinetic energy initial minus the kinetic energy final. And that would be before and after. So it'll equal to 16 minus 8, which is 8 joules for the total amount of energy transferred. And lastly, a chicken is running in a circular path with an angular speed of 1.5 radians per second. How long does it take the chicken to complete one revolution? So this question is pretty simple. We're just going to have to follow an equation, and that is 2 pi over the angular speed. Let's do, which is given to us, which is 1.52. So we're just going to input that into the calculator and we get 4.13 seconds. And this equation right here is equal to the angular speed. And that's how, this is how long it takes the chicken to complete one revolution.